Good morning, gents. My name is Christopher Moss, and this is going to be our first session of the molecular representation chapter. Now, take a few seconds to look over the materials we'll be covering today. On our left are some materials that I suggest you study from Gen Chem that pertains to this lecture. And then for this session, we're going to be covering bond line structures, the rules of drawing the bond line structures and how to read them, and then some functional groups that we'll start practicing to recognize. Now, to start off, what's a bond line structure? A bond line structure is a simplified way to draw organic molecules where bonds are represented as lines between those atoms, and then the corners and the endpoints that we see here are carbon atoms. Now, in chemistry, we have a multitude of ways to describe our molecules, starting off with the molecular formula, which gives us the number of atoms that are inside that molecule, condensed formulas and partially condensed formulas that give us an idea of the arrangement of those atoms, and then Lewis structures, which gives us every single atom, its bonds, and the lone pairs of that molecule. However, in organic chemistry, we start to deal with larger molecules and with a lot of hydrocarbon tails. And as the bigger it becomes, the more tedious it is to draw a Lewis structure. So to fight against that, we use what we call bond line structure, where carbon atoms and the hydrogens that are attached to them are omitted, simplifying them. Now, to draw bond line structures, there's a few set of rules that we have to follow. The first rule is that sp3 and sp2 hybridized atoms are drawn in a zigzag format. Now, what does that mean? Take a look at the drawing on the right. So I draw a few forms of butane. In butane, we have only single bonds. So all the atoms drawn are sp3 hybridized. We can draw them in a zigzag as such. The one below, we have 2-butene. So the first and the fourth one are sp3 hybridized, but the second and third one are sp2. It is still drawn in that zigzag format. The reason being both of these work are because the zigzag format is a good representation of the molecular geometry given by the hybridization. But sp3 typically has a tetrahedral structure, while an sp2 has that trigonal planar. Both of them are best represented in that zigzag. Now notice, for sp hybridized atoms, it gives us a linear geometry as such. Now, before I make you guys fall asleep, we're going to go to the second rule, which is that the bonds drawn should be spread out evenly. Now, this obviously makes it a lot easier for us to see how, the atoms that are drawn in that structure, but it also gives us an accurate representation of the bond angles of that structure. The third rule is that when you draw your single bonds, so sp3 hybridized ones, that the way it branches out or it faces are irrelevant. Now, what does that mean? Now, let's take a look at the drawing on the right. I have two identical molecules, believe it or not. Now, let's call the number of atoms. So we have 1, 2, 3, 4, 5, and 6 carbons. The way I counted them is that we have 1, 2, 3 endpoints, right? And then 1, 2, 3 corners. So a total of 6 carbons. And then the one on our right, we have 1, 2, 3, 4, 5, and then 6 carbons. Now, if we take at first glance, oh, it's facing it a different way, these must be different compounds. Now, I wouldn't blame if that was your answer. But in reality, they're actually the same molecules. The carbon that's sticking out of here sticks out from the third carbon, and the same goes for this one. The number of hydrogens, if you follow the rules for formal charge, they're all the same, so they both have the same number of hydrogens. So that's just one thing to keep in mind when you recognize when they give you those two and say, are they same or are they different? Now, the fourth rule is that all heteroatoms, so that means any atoms other than carbon and the hydrogen that's attached to the carbon must be drawn. Hydrogen atoms attached to those heteroatoms must be drawn as well. Now, this has to do with the formal charges, as that even though they might have a formal charge of 0, they can have the different numbers of bonds and lone pairs and you can still satisfy with them. Carbon just so happens to require 4 bonds to maintain the octet and the formal charge, which is the reason why we don't draw any hydrogen atoms sticking out of there, because we can always assume so. Oxygen and nitrogen, on the other hand, can follow different ways. So for example, oxygen can either have 2 bonds and then 4 lone pairs like this and have a formal charge of 0. But it can also be drawn with a hydrogen. So one with hydrogen, another one with hydrogen, and then 4 lone pairs. The problem with this is that if we decided not to draw the hydrogen atom and just show that it's sticking out like that, we're not really sure if it has 6 lone electrons or it has a hydrogen that attached to there to make the bond. Same rule applies with nitrogen. Now, the fifth and the most important rule, hopefully you guys are still paying attention, is that you should never draw more than 4 bonds to a carbon atom. This is something you'll never ever see, at least in the undergrad level, where you see more than 5 bonds drawn to a carbon atom. So please do not break this one. It happens a lot more often than you think. Now, functional groups. Functional groups are basically a common, just like the polyions we learned in Gen Chem. These are some things that you have to recognize and memorize and then start to recognize within those structures. Organic compounds can possess a group of atoms that have unique properties that are shared among different molecules. Now, learning them might be a challenge, but with proper practice, you can develop pattern recognition easily identifying them. So on our right, I directly took it from my notes, are some of the common functional groups that you will see in organic chemistry. Some of them, like alcohol, alkene, alkyne, thiol, amine, maybe amide, might be easy to recognize. But things like ether, sulfide, ester, and the other carboxylic acid derivatives might be a little bit challenging to find. But like I said, we'll do some practice problems later, and I can also share you a website where it has some large organic structures to help you practice with those skills. All right, that's about it for now.